Hi everybody, this is Cal with sections 15.4, double integrals in polar coordinates, and 15.5, applications of double integrals. So, we're going to start with double integrals in polar coordinates. Your book starts on the bottom of page 1021 with just a quick little refresher of my words are not working. A quick refresher of like how polar coordinates work, how to get back and forth between rectangular and polar coordinates, and you want to make sure that you know these three equations right in here. They all come from the picture on the left, figure 2. The book brings up polar rectangles, and I do absolutely want you to know what a polar rectangle is and what sorts of things they look like. Figure 1 is a couple of examples. Figure 3 is another example. And what your book does on page 1022 is kind of develop an integral using polar coordinates. You don't have to pay too much terrible attention to this. You can kind of see the basic idea of what they're doing. They're dividing into polar subrectangles. They're finding the value, the average value of your function over each and adding up all the values, the same way that you do for an integral in general. If you read through this carefully, you'll see that as you do this, there's an extra factor of r that pops up, and this shows up in our general equation. You need to know this, that to change to polar coordinates in a double integral, you plug in your polar conversions, x equals r cosine theta, y equals r sine theta, and then you get this extra factor of r before your dr d theta. That's extraordinarily important. If you forget that, that's a big... Excuse me. That's a big problem. So anyway, I want you to go through example 1 pretty carefully. Make sure you understand what's going on there. Example 2, same kind of thing. Make sure that you understand what's up over there. And square 3 over here, that's pretty good. I mean, this gives you the general form for an integral over a polar region. The takeaway, I mean, this should not be a shock. The takeaway here is that we almost always do dr before d theta. I don't know why, it just kind of ends up that way. The little blurb below this says something about finding the area of a polar region. Example 3 shows an explicit example of that. And example 4 is a more generalized example of working in polar coordinates to find an integral. In general, you just want to think of polar coordinates as a good tool for integration in certain circumstances. This is definitely in my standard lexicon of things to try. Makes a lot of integrals a lot easier. So, pay close attention to the examples in this section. You don't have to pay so close attention to the theory, especially the double Riemann sums, that sort of thing. So, that ties together section 15.4. Let's move straight into 15.5, which is applications of double integrals. And we're not going to do a heck of a lot of this section. I do want you to read the part on density and mass. I like these examples with, if you have a thin plate or what we call a lamina with a density function, then you can calculate the mass of it by integrating the density over the lamina, which you see here in square 1. Example 1 is a good example of how that works. They're using charge distributed over a plate. I do want you to understand moments and centers of mass. So read through that section pretty carefully. Make sure you know the formulas. Example 2 demonstrates an action, as does example 3. That's finding the center of mass. And I also want you to read moments of inertia, which is also pretty straightforward. There's a formula for it. And example 4 shows that in action. And that's actually all that we're going to cover in this section. You might think about reading the rest of the section on moments of inertia, but I'm not going to ask you about radius of gyration or anything like that, and we're not going to go into anything in probability or later. So that's everything for section 15.5. So that's all. Have a good one.